Hey everyone, alright, so this video is the pH scale and power of hydronium. This is the second video. My first video was the indicators. I think I might have fixed a couple of the weird problems that I had in that video. Keep in mind I'm still kind of learning how to do this. But yeah, so I'm going to try and fix some of the mistakes that I think I made in the first video. But anyway, the overall idea is that I'm going to go over the pH scale, what it is, what it means, and how it is that we came to come up with the pH scale. But yeah, so I'm going to be following, let's see, I think in your packet, this is page 4, it looks like. Yeah, so I think this is page 4. It says Topic 2 pH scale. So that's what I'm going to be looking at. That's what I'm going to be going through if you want to follow along. But yeah, let's go ahead and get started. Okay, let's bring this back over here. So we're all the way down here. Cool. Okay, so pH. Sorry, my cat unplugged my iPad, so that kind of died on me really quick. But yeah, I also realized, just looking back at it really quick, my pen is making a giant slapping sound against the iPad, so I guess I apologize for that. I don't really know how to fix that one, so you're just going to have to deal with the slapping sound. So just enjoy this sound, because you're going to hear this probably a lot in every single video that I make. But yeah, anyway, so the pH scale, I'm sorry. The pH scale, technically, if you take a look at this right here, so notice how the P is lowercase and the H is uppercase. That kind of has to do with hydrogen. So hydrogen, like P, kind of stands for concentration here. That was the greatest concentration that I've ever written in my entire life. Yeah, alright, so P kind of stands for concentration. So pH means the concentration of H, or hydrogen. And specifically, we're talking about the H plus ions that something has. So the more hydrogen ions that something has, the more acidic it is. The concentration-wise, the less hydrogen ions that something has, the more basic it is. Let me show you a little bit closer what that kind of means. So let me just erase this really quick. The scale, if you remember the scale a little bit, the scale should go from 0 all the way up to 14, like that, with 7 in the middle. Most people can remember that water is neutral, and that kind of sits right around a 7 pH. And just to bring back a little bit of what we did in the indicators video, everything in between 0 and 7 is acidic. Everything between 7 and 14 is basic, and water is considered neutral at about 7. So what we're talking about when we're talking about the pH scale is we're talking about, like we said, the H plus ions. Now, some of these things, like for example acid rain or I don't know, orange juice or any of those things, it doesn't just have H plus in it, it also will typically have an OH minus or a hydroxide ion as well. And depending on the concentration between these hydroxide ions and these H plus ions, it determines whether something is acidic or basic. So the way that it goes is if something has significantly more H pluses than OH minuses, so like maybe I'll do this right here, so like H pluses, and I'll do like OH minuses. So let's say that we have a lot of H pluses and only a little OH minuses. That means we have way more of these. That means that we are acidic. If I were to undo that, and maybe I don't have a lot of H pluses, maybe I switch it a little bit. Here, let me just get rid of this real quick. Okay. Maybe I have very little H pluses and many hydroxide ions, that would mean that I'm basic. Now, when most people understand that water is neutral, they kind of think like, oh, okay, water is neutral because it's not an acid and it's not a base. It's actually not really the way that it works. Let me just rewrite that really quick. Water is basic because the concentrations of both H plus and OH minus are about equal. So it's almost like water is an acid and a base at the same time. It's got H plus ions and it's got OH minus ions, which makes it right in the middle, neutral. And if you think about it, that kind of makes sense, because if I take, for example, like one H plus ion and I add it to a hydroxide ion, I get water. H plus OH minus yields water. So when water breaks up, it can break up into a hydroxide ion or an H plus ion. Okay, so let's get rid of all of this. I'm going to be super awkward and very slowly erase everything, because what was happening in the last video was I was using the undo button to erase things. So like I would write something and I would then hit the undo button, and it wouldn't just undo it. I don't know. I don't know if it makes sense to you, but it wouldn't just undo that I wrote it. It would undo that I put it down, which meant you hear the sound like this of me writing it, but you don't see anything being written. And then there was like some weird stuff where, like, I don't know, things were being written and I had to type them in. It was super annoying. So I think I fixed it, but that just means I have to awkwardly erase everything I write. So bear with me. But anyway, so here, if we go over to the next page, in neutral water, the concentration of H plus is 1.0 times 10 to the negative 7th molar. So the pH is. Now we already know what the pH of water is. We kind of already said it. The pH is 7, but that little power right here, that negative 7, that kind of shows you like you can express the concentration of H plus ions in scientific notation, and this power can tell you what the pH of water is. So let's see. If we take a look at these flasks, it says below each diagram, describe each flask as acidic, basic, or neutral. So what we want to do is we want to take a look at these flasks, and we want to say, all right, if I look at flask number 1, for example, so I'm right over there, let's see, I see 1 H plus ion, I see 2 H plus ions, I see 3, I see 4 H plus ions, right? So that's one thing that's an acid, 2 things, 3 things, 4 things. And as far as bases go, I see an OH minus, an OH minus, an OH minus, an OH minus. I have 4 of each. That means that I should be neutral, because I have approximately an equal concentration of hydroxide and H plus ions. Does that kind of make sense? I hope. Maybe. I mean, you can't really talk to me. I guess that was a dumb question to ask. Let's just awkwardly go on to the next one. I've got, as far as acids go, H plus, H plus, H plus, H plus, H plus, and I've only got 2 hydroxide ions this time. So I have 5 H plus ions. That's way more. That's going to mean that this thing is acidic. If we keep going, I've got, let's see, a couple of bases. I've got OH, 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 OH. This thing here, that's hydronium, H3O plus. In case you've forgotten, H3O plus is just water with an extra hydrogen ion. So it still marks something that's acidic, but I still only have, I only have one hydronium ion here, and it looks like I have 6 hydroxide ions. So that's definitely going to be basic here. Here I've got hydroxide, hydroxide. That's hydronium. That's two hydroxides, 1 hydronium. That means we're going to be basic here as well. I'll just put little arrows just because I'm lazy. Down here on the bottom, now this is a little bit different because now we have the actual concentrations. For example, I have 1 molar, 1.0 molar hydronium, and I have 1.0 molar hydroxide. Those concentrations are the same. That makes this thing neutral. Okay, moving on, number 6. I have 5.0 molar hydronium, and I have 10.0 molar hydroxide. My hydroxide ions, the concentration is much higher. It's double whatever my hydronium is. So this thing is basic. Okay. This one, again, we're getting a little trickier because now we have it in scientific notation. This looks like, what does that say, 1 times 10 to the negative 16th? Yeah, and that's my base down here, 1 times 10 to the negative 9th. So I have to figure out which one is the bigger. So, like, if this helps you, let's do this down here. If this helps you, you can change these into standard notation. If you really wanted to sit here and do that, you could do 1 times 10 to the negative 16th, and you could say, oh god, okay, so that means I have to move my decimal 16 spots to the left. Oh my god, that's like a lot of spots. I don't really want to do that. That's a lot of work. So you can just compare the numbers, for example. Like, let me do this. So we got 1 times 10 to the negative 16th, and I have 1 times 10 to the negative 9th. Careful, because these are negative exponents. So the one that is actually the larger number is this one here, because I only have to move it 9 spots to the left. So that means, what is that, like 3, 4, 5, 6, 7, 8 with a 1? That's times 10. That's 1 times 10 to the negative 9th. If I wanted to go all the way to the negative 16th, Jesus, I would have to go, let's see, 10, 11, 12, 13, 14, 15, 16? I'm like all the way in my number here, Jesus. All right, like 0, it's 9, okay. I would have to move that decimal place all the way out here, which is a way smaller number. So 1 times 10 to the negative 9th is definitely the larger number. That means that because my base is a larger number than my acid, the concentration is higher. That means I am also basic in this flask. And if we take a look at the last one, we've got 1 times 10 to the negative 3 molar hydroxide. Oh, I used the wrong color. That was the whole point. It tricked me. 1 times 10 to the negative 3 molar hydroxide, that's our base. And then our acid is 1 times 10 to the negative 11th H plus concentration. Again, this is a negative exponent. You got to be careful. The larger number is going to be this one, because it only has to move 3 spots to the left instead of 11. So that means this last flask is also basic. So that's like the short and sweet version of, as far as concentration goes, how to tell whether something is acidic, basic, or neutral. If it has more pluses, whether that's H plus or H3O plus, so hydrogen ion or hydronium ion, if it has more of those than anything else, then it's acidic. If it has more hydroxide ions and negatives, that means it's basic. If it has the same amount, that means it's neutral, just like water. Okay, let's take a look here. I think yours has something like this as well. Let me just look at it. Okay, all right, so mine got a little cut off, it looks like. But yours should have something that looks kind of like this. This can kind of also help you understand a little bit about what I'm talking about when I talk about the negative exponents. So like if we look up here, right up, oh, that's hydroxide. So this, I think the top side for you guys, I think that says hydroxide, right? Yes, hydroxide. So actually here, let me use the actual colors that I used before. And down here it says hydronium, or actually yours just says hydrogen ions. So let's just keep it the same. Hydrogen ions. I think this one, it goes like all the way over here. Look at what a good artist I am. Oh, I'm enjoying this way too much. All my straight lines too, this is great. I don't really want to draw the rest of it, if we're being honest. But, here, let me show you. So the idea is that all the way over here, a pH of 1, we should know that that's an acidic solution, something that's acidic, right? That means it's got way more hydrogen ions than hydroxide ions. And notice that the negative exponent for the hydrogen ions down here is lower than the negative exponent for this one. So in a pH of 1, that means we have hydrogen ions in a way higher concentration than our hydroxide ions. If you were to go to the other side of the pH scale, I'm just going to use 8 because that's what I have like right here, but your side should be all the way up to 14. It's not that it matters that much, but in a pH of 8, for example, we've got, that looks like times 10 to the negative 8th, and this one is times 10 to the negative 6th. Good. So here again, now we have the basic side, the hydroxide side, has the negative 6. That's the lower exponent. That means that it has a higher concentration. If we have more hydroxides, that means we have less hydrogen ions, which means we have a basic solution, like 8. Basically, the thing you need to keep in mind is that if you have a higher concentration of H pluses, just like up here, ooh, there we go, a higher concentration of H pluses, like up here, that means it's acidic. If you have more OH minuses, that means it's basic, and if you have the same amount, that means it's neutral. Let's keep going. Alright, so let's take a look at these, because you have these questions as well, and it's definitely worth knowing how to do. So it says when the concentration, alright, so let's start with this one. When a pH, so we got a pH of 0 to 7, we should know that that's acidic. A pH of 7 on the dot, that means neutral. Yep, wonderful handwriting, as always. When the concentration of H plus is 10 times negative 1 molar, the pH, so if I look up here, right there, if my hydrogen ions, my pH is times 10 to the negative 1, that means my pH should also be 1. When it's 10 to the negative 2nd molar, that means my pH is 2. So that little exponent can help you tell what the actual pH is. So it's very useful to pick that up, I think. I think that's your page. Let's go on the next one here. So we got up here a pH of 7 to 14. That is basic. And 10 to the negative 3rd molar, that's a pH of 3. Definitely things we need to know. Now the reason, so like you might not, most people, especially even if you know a little bit about the pH scale, most people don't know like how the pH scale works. Like most people aren't familiar with the fact that the pH scale measures hydrogen ions. That's just not something that we talk about. Instead of talking about the hydronium concentration versus the hydroxide concentration in pool water, for example, that's a little difficult for normal, like, common language. So we came up with this pH scale, which kind of simplifies whether something's acidic or basic or neutral. The important thing to keep in mind is that every step on the pH scale, let me just get rid of that really quick. All right, so every step on the pH scale is what's called like a fold. So like, for example, like right here, if I start at a pH of 4, which we know is acidic, and I'm going to a pH of 2, which is even more acidic, that's a decrease in pH level. So we've gotten more acidic here. So that's like the first thing that I kind of want to point out here. So we're getting more acidic. We're getting more acidic by 2 pH places, right? We're going from 4 to 2. That's more acidic. Every step on the pH scale is a times 10 difference. So like, we're getting more H pluses because we're getting more acidic. We're going from 4 to 2. That means we're getting more acidic. That means our H pluses are increasing. And they're increasing every single time we go down a step. So like, if we're looking at the pH scale, right, like this is 2, this is 4. In between 2 and 4, we should have 3, right? When we go from a pH of 4 and we go to the 3 place, that means we are increasing our H pluses by 10 times. Sorry. When we go from 3 to 2, we are increasing our H pluses by another 10 times. That means in total, 10 times 10 is 100. We are increasing our H plus concentration by 100 times. This also works in reverse. The tricky part is making sure that you're not saying it's an increase, but maybe a decrease. Again, let me kind of explain. I'll show you a quick example, and then we'll go over some like practice questions that I guess we have down here. If, for example, let's say that instead of going from 4 to 2, let's say we were going the other direction. So let's say we were going from 2 to 4. We start at a pH of 2. Let's even just also cross this off just to get this out of our way. We're going from a pH of 2 to a pH of 4. Now we're not getting more acidic. We're still an acid in both pHs, but instead we're getting less acidic. Getting less acidic here. Okay, so our H plus concentration is not increasing, it's decreasing. And again, if we were to take a look at our pH scale, right? So this is 2, this is 4. We've still got 3 in the middle here. When I go from a pH of 2 to a pH of 3, I'm decreasing the H plus concentration by 10 times. And then when I'm going from 3 to 4, I'm decreasing the H plus concentration by another 10 times. That means 10 times 10 is 100. We are decreasing our H plus concentration by a total of 100 times when we go from pH 2 to pH 4. That is like it's a really quick explanation of how that works. I want to go through some of the practice questions that we have down at the bottom. Maybe that'll help clear it up for you if that wasn't a very good explanation. Let's take a look. It says a solution with a pH of 3 is 10 times more than a solution with a pH of blank. Well, we know that 10 times, so hold on, there we go. We know that a solution, like if we're, it doesn't matter whether we're increasing or decreasing, 10 times means that we've gone one step on the pH scale. We've either gone one step up or we've gone one step down. And what this is saying is that a solution with a pH of 3 is 10 times more acidic than. That means we need something less acidic. And that's not going to be a pH that's lower, that's going to be a pH of higher. So that means we're looking for the pH that is 1 step higher than something with a pH of 3. That's a pH of 4. Something with a pH of 4 has 10 times less H plus ions than something with a pH of 3 because it is 1 step less acidic. Okay, a solution with a pH of 3 is blank times more acidic than a solution with a pH of 6. So even though the question kind of says it, we're definitely more acidic because the pH of 3 is lower on the pH scale than the pH of 6. We need to figure out how many more times though. Well, 3 is 3 steps lower than 6, right? If we go from 3 to 6, that's 3 steps. 1 step is 10 times more acidic. 2 steps is another 10 times more, and 3 steps is a third times 10. So 10 times 10 is 100, times another 10 gives us 1,000. We are 1,000 times more acidic than something with a pH of 6. Letter C, we have a solution with a pH of 2 has a hydronium ion concentration 10,000 times greater than a solution with a pH of blank. So we've got a pH of 2, and it is way more acidic. We have to figure out how many steps 10,000 times is. Well, if we take times 10, that's 1 step, right? Times 10 again is 2 steps. And times 10 again is 3 steps. That gave us 1,000 before, right? Well, we need 10,000. So let's go times 10 a 4th time. That is 10,000. So that means that we've gone 4 steps on the pH scale. And obviously, I mean, we're not going to be going down the pH scale 4 steps because we're only at 2. But the question says that pH of 2 has a hydronium concentration of greater than, which means we should be going less acidic, as in we should be going up the pH scale 4 steps. That means that the pH that we're looking for is a pH of 6. Okay. If we take a look down here, we've got D and E. It says a sample of base has a pH of 9. What would the pH of a base 1,000, that should probably be 1,000 times, well, that doesn't look right, hold on. 1,000 times, oh, can't write, please save me. Okay, a sample of base has a pH of 9. What would the pH of a base 1,000 times more basic be? So just like that last problem, we actually have to start by figuring out how many steps we go. Well, if we've got 1,000, kind of like, what was that, letter D? Or, I'm sorry, letter B. It says, let's see, if we have times 10, and we have times 10 again, and we have times 10 again, if we do that 3 times, that gives us 1,000. That means that we're talking about 3 steps on the pH scale. Because 10 times 10 times 10 is 1,000. Now this one is saying that you start with a pH of 9. And it's saying we're looking for something 1,000 times more basic. You got to be careful here. So if we're saying more basic, that means not three steps like lower on the pH scale. We're talking about 3 steps higher on the pH scale. A base is high pH. So that means we have a pH of 12. That's 3 steps higher on the pH scale. This one says a sample of acid has a pH of 3. What would be the pH of an acid 100 times more acidic be? All right, so we've got a pH of 3. That's probably important. 100 times more acidic. Well, we got times 10 is one step. Times 10 again is a second step. That's our 100 times, right? So that means 2 steps on the pH scale. And the question said 100 times more acidic. That means down the pH scale, which means our pH should be a pH of 1. Starting to get the hang of it? I hope so. Let's try these. So these are Regents questions. Not that these aren't up here, not that the ones that we've done aren't Regents questions, but the way that the Regents can word them can be a little bit different. So for example, it says, which statement correctly describes the solution with a pH of 9? Well, if we have a pH of 9, I should immediately probably think, is this a base, is this an acid, or is this neutral? This particular solution with a pH of 9 is higher up on the pH scale. That means we're talking about a base. It's higher than 7, that means this thing is a base. So if it's a base, should it have more OH minus ions, or should it have more H plus ions? And again, when I say H plus ions, I could also be talking about hydronium, H3O plus, because the only difference between these two is that hydronium has water. So both of these things are kind of like the same. When you see a plus sign, you should think acid, and when you see a minus sign, you should think base. So what the question is saying is, which one accurately describes a solution with a pH of 9? And like we said, a pH of 9 means a base. So choice A says it has a higher concentration of H3O plus than OH minus. Well, we already know that that's not right, because a base should have more OH minuses. So it's definitely not going to be this one. It says it has a higher concentration of OH minus than H3O plus. It says it also causes a litmus to turn blue. I'm not really 100% sure about that yet, but it could be this one. So let's leave this one. Choice C says it has a higher concentration of H3O plus than OH minus, and I don't even have to read the rest of it because I already know that that's not true. The last one says it also has a higher concentration of OH minus than H3O plus. It says it also causes methyl orange to turn red. So now I'm at a point where I know that the OH minuses are going to be greater than the H3O pluses. So that eliminated 2 answer choices. This next part, hopefully you recognize this as an indicator question. So what we're going to need is our reference table. Sorry, I'm just pulling mine up right now. Okay, handy dandy reference tables. If you're not already scrolling to the acid-base indicator table, you should probably do that. So I'm gonna pull this kind of like in the indicator video. I'm just gonna put this like over here somewhere. Okay. Table M is where our indicators are. We're talking about a base, right? So a pH of 9. So it's either going to cause litmus to turn blue or methyl orange to turn red. And we got to use table M to figure that out. So if I look at table M for litmus, right over here, it says between 4.5 and 8.3. That's the range for litmus, and it changes from red to blue. And as a quick review, that means if the pH is lower than 4.5, litmus will stay red and not change color. And if the pH is higher than 8.3, that means the litmus will change to blue. Somewhere in between that 4.5 and 8.3, there will be a color change. But the idea here is that we have a pH of 9, so that's higher than this pH range. If that's higher than this pH range, we should definitely be the color blue. So that already kind of looks like the right answer, but let's just check the other one just to make sure we didn't make a mistake. The other one says methyl orange turns red. So methyl orange is right here. This is the pH range for methyl orange, 3.1 to 4.4. Again, that means that any solution lower than 3.1 is going to stay red, and any solution higher than 4.4 is going to turn to yellow. And with a pH of 9, that means methyl orange shouldn't stay red, it should turn to yellow, and that's not what the answer says. The answer says it causes methyl orange to turn red, and I can already tell that that's not right. So it's definitely not that one. That means the only one I'm left with is choice B. Cool. Okay, I think there's a few more. Oh, let's get situated here. All right, beautiful. So the last couple of questions, topic 3 is going to be a different video, but let's do these last two, and then that'll be it. It says, which pH change represents a 100-fold increase in the concentration of H3O+. All right, so this is going to be this fold question again. All right, cool. So we're talking about a 100-fold increase. Let me just switch over to there we go. 100-fold increase. 100-fold increase, that means we're doing times 10 twice, right? That's 100. 10 times 10 is 100. That means 2 steps on the pH scale. So that means we need to have something change by 2 steps. So I can already eliminate a couple of answer choices. I'm looking at choice D, that's only 1 step, right? And I can also see choice B is 13 to 14, that's also 1. So now, if you notice, there are 2 answer choices. Both of them have 1 step, but one of them, choice A, goes up the pH scale, and choice B goes down the pH scale. So this is kind of testing your ability to understand that if we increase our H3O pluses, we should be getting more acidic. If we're getting more acidic, that means we're going, that was the worst arrow I think I've drawn in my entire life. Not much better, whatever. If we're getting more acidic, that means we are going down the pH scale. God, I can't write with this thing. Like, it somehow makes my handwriting worse. I don't understand. I never knew that was possible. All right, so if we're getting more acidic, that means we're going down the pH scale. That means we're going to be this answer right here, choice C. Okay, so which of these 1 molar solutions will have the highest pH? Oh, this is a good question. Let me get rid of some of this here first. So just while I'm erasing that, the highest pH, that means a base. High pHs mean base. I'm going to need my reference tables again. Sorry, I have to search it every time I switch a slide. Let's click it over here. All right, cool. So again, we should be looking at table M, all the way where our acids and bases are. Oh, I'm sorry, not table M. But this is the page that we're going to need. Here, we're going to need to look at tables K and L. So I'm going to move this over here. Okay, so which of these 1 molar solutions have the highest pH? Just so you know, the 1 molar that they put here, totally unimportant. This doesn't really mean anything. You can ignore it. We don't even need it. Which of these solutions has the highest pH? If I look at my acids and bases table here on the right, I can see that NaOH, right there, actually, I'm going to put that in blue because I can see that that is a base right here. HCl is an acid. That's all the way over here, so I know it's not that one because it's definitely not a base. NaCl is just a salt, so that's not that. And let's see here. We've got CH3OH. I'm taking a look. I do not see it here at all at any of the tables. So yeah, it's not going to be that one either. And again, just as a quick reminder, because this is meant to kind of confuse people, a lot of people look at this and they say, hey, I see an OH, why isn't that a base? As a reminder, anything with carbon in it, at the front especially, if there's an OH attached to it at the end, that means it's not a base, it's an alcohol. We'll talk a little bit more about alcohols when we get to organic chemistry, but for now, those are like the trick answers for a little bit. Just make sure you're checking your tables, K and L, because they have all the acids and bases there that you need. So yeah, that means it's going to be choice A, NaOH. Alright, so that's the acids and bases video, and that's the pH scale, so I hope that helped a little bit. The next one that I make is going to be right here, topic 3, acid and base neutralization. Some classes might have already done it, some classes might not have. I'm going to make it because I definitely want everyone to understand the idea, and yeah. Remember to like and subscribe for more chemistry videos. But yeah, I'll see you guys in the next video, except I won't see you. Why do people say that they're going to see you in the next video? Because you see them and they don't see you. I'm going to stop talking.